Look at the mathematics behind the Young's double slit experiment now. We're going to define a couple things, introduce an equation to you, and that should get us on our way. So we talked about how Young's double slit, or just a double slit in general, or two-point source interferences, are going to give you this kind of pattern where you have a bright spot, and then you have other bright spots that are going to have less brightness or less intensity, at least when it's due to diffraction like this. So we talked about that in the last video. And you can see the naming conventions here. So this is the 0th fringe, and then the first fringe, the second, the third, or the first order, second order, third order brightness. But it's not just bright fringes that we look at. We also look at the dark fringes. And instead of going 0, 1, 2, 3, it's actually normally like 1/2 for the first dark fringe, 3/2 for the second dark fringe, 5/2 for the third. And you can see that 1/2, right? 0.51, 1, 1.52, 2, 2.53. That's where it comes from. It actually comes from what's happening over here. All right, so if we erase this, we can look. So the center bright fringe comes from the rays. Right? If we look at these as rays, they're both going to come here and they're going to be constructive, and you're going to get that bright spot. In general, for the bright spot to happen, there has to be constructive interference, which means that the length that this one travels, this first ray, and the length this second ray travels, they don't have to be the same, but when you look at the difference between the two, the difference should work out to be some number times the wavelength, right? If you have, let's say you have a wave and you have a second wave, if you want these to add, these two spots, if I can draw it, these two spots need to line up. Now, these waves are continuous, right? This goes on and on. So it doesn't really matter which part of the wave, as long as it is the crest, or which crest of this continuous wave, as long as it's a crest. And so the same applies if we want to go ahead and find a dark fringe. You're going to want this difference to be some number times half the wave, right? You want half a wave in between. So if you have a crest, then you're going to want a trough to line up, and vice versa. And this will give you your destructive interference. And that's why you can see this decay, right? Maximum constructive here, maximum destructive here. In between, it's a mix, right? You're getting some difference, but it's not an exact or in between. And so this change in length is normally referred to as the path difference. And so what is the path difference? The path difference is quite literally how much further one has to travel than the other, than these two rays, right? And we're talking about rays, there's an infinite amount of these rays that are going. And that's why you get all these interference patterns when we're looking at only two rays. So if two rays are relatively parallel, right, they're going to hit the screen like this. And the path difference that we're looking at is this little section right here. All right, that's our path difference. And our path difference, like we said, delta L, right, is just L2 minus L1. And this has two outcomes, right? If we want a bright spot, it would be n times lambda. If we want a dark spot, it's going to be n times lambda over 2. Now, if we look at this, we can see that this distance, d, and d is the distance between the slits, okay, we should define that. Then this path distance, or difference, delta L, is just going to be d sine theta, right? And theta, we can define that, is the angle of the ray with respect to a horizontal line to the surface. All right, so we should actually write that as a script. We can combine these two now into one equation. And the way that equation is normally written, and the way I believe it's written in your reference table, is d sine theta is equal to m lambda. Now again, this is just your path difference, delta L. That's all that this is. Okay, these are exactly the same. And I use the script L for this because L is often referred to as this, the length between the screen and where your slits are, or your openings. Right now, M, okay, that's the fun part. M is our N and our N over 2. So you have really two choices. I've seen it written a bunch of different ways. So if it's a bright spot, then M is just equal to 0, 1, 2, 3, so on. And if it's dark, M is equal to 1/2, 3/2, your 5/2, and so on. All right, the other way that I've seen it written is M or M plus 1/2, depending if you want bright or dark. But you really just have to think about what you're looking for. Do you want your path difference to be a whole number of waves, or a phase shift of either 0 or 360? Or do you want your phase shift, your path difference, to be half a wave, okay, 180 degrees? That way you get the full destructive interference, right? So if we go back up here one more time and just take a look at this, right, this is your max, your full. So this is 0 or 360 degrees between. This is your 180 degree phase shift, okay, where you have your crest matching your trough. But in between, okay, just one more time, is where this thing is, slightly offset. Okay, where you have your wave, it kind of looks like that. All right, it's slightly offset, and you can actually continue to move it, and as you move it, it'll come in and out, right? So now we're down here, and you move a little bit more, we're getting closer to this peak, and then you get that peak, and so on and so forth. And so let's actually just take a look at a problem now. All right, so red light, 664 nanometers, is used in Young's experiment. All right, so we're recreating this experiment. The slits are separated by 1.2 times 10 to the negative fourth meters, and the screen is located 2.75 meters from the slits. And so what we want to know is its distance y. Where is this third order bright fringe? All right, and so the equation we know is d sine theta equals m lambda. And so a couple things we know, right? Lambda is our wavelength, and as it goes through, that wavelength doesn't change, whether it's on this side or this side, that stays the same. We know d, that's from here, and we actually know m too, right? This is the third order, and so in that case, m is going to be 3. And so we can fill this out, right? D will be the 1.2 times 10 to the negative fourth meters sine of theta, and we don't know theta, and m is going to be the third order because it's bright, so it's a whole number, and then our wavelength is going to be 664 nanometers, or 664 times 10 to the negative ninth meters. Now, what's the whole point in doing that? It should be pretty clear that if you look at this, we know this length, we want to know this length, we can find this. Because if you look, right, this height would just be L tan theta. All right, tan is opposite over adjacent, and that's why we can use that. And so if we go in here now, we can solve for theta. Theta will just be the inverse sine of 3 times 664 times 10 to the negative ninth divided by the 1.2 times 10 to the negative fourth. And theta will therefore be 0.951 degrees. Right, really small angle. Then we can go in here. So y is just going to be equal to L, which is 2.75, times the tangent of 0.951 degrees. And when you do that, you should see that y is equal to 0.0456 meters. Right? Really small distance between the third and the first. And these are evenly spaced, so you can easily find where the second would be, and you can easily find where the third would be, right? That would just divide this in 3. And so you can actually find the spacing between each one. You can predict what these peaks would look like, right? So it would look like something like this. And that would continue on. And it would look the same on this side. You have your bright spot, and then you have your dark spot. Bright spot, dark spot. And actually, I drew that incorrectly. The third fringe is over here. All right, so you'd have your, yes, 0th, first, second, third. So actually, I think I had that correct. All right, but that's where your bright spots will be, and that's where your dark spots will be. All right, on the next video, we'll just work through a problem.